Hey everybody, I'm back with another video on statistical power. This time we're relating it to sample size as we do significance testing. This discussion is going to mirror some of the things that we talked about when we were doing sample size for confidence intervals, but now things are, of course, more complicated and therefore more fun. So often when we do a significance test, we want to specify both a low alpha and a low beta. That is, we want our test to be both powerful and significant. As you might expect, we can accomplish those goals by getting a larger sample. Let's walk through this with an example. So suppose we have a null hypothesis that mu is 150 and an alternative hypothesis that mu is less than 150. And we know that the population that we're sampling from is going to be approximately normal with standard deviation of sigma equals 25. We're going to want to require alpha equals 0.05 and a beta of 0.10 when mu is 140. So remember, of course, that beta is going to depend on mu. We have to specify the mu that we're talking about. What kind of sample size will get us there? So we're going to take this in pieces. First, we're going to consider alpha, then we're going to consider beta. They're both going to give us some information about n. So when we're talking about alpha, we're going to assume that the null hypothesis is true. This is how we progress when we do a significance test. So if h naught is true, then x bar is normal with mean 150 and standard deviation 25 over the square root of n. We're talking about a one-sided significance test, so we're going to have a rejection region there on the left somewhere, x bar less than c, for some c that we just don't know. We can write an equation. We want that area, alpha, to be 0.05. We want that shaded area to be 0.05. We also know that it is the area to the left of C in the normal distribution with mean 150 and standard deviation 25 over the square root of n. So I can write a normal CDF statement. The phi of C minus 150 over 25 over the square root of n equals 0.05. The inverse CDF of 0.05 is going to be negative 1.645 for the standard normal distribution. And then I solved it for C, and I got an equation in terms of n. So we have two variables here, or two constants, we need to solve for, so we're going to need another equation. Fortunately, we haven't considered beta yet, so let's do that. So when we're talking about a type 2 error, we're talking about assuming a different true population mean, in this case 140. And we know that if mu is actually 140, then there's a 10% chance that the null hypothesis isn't rejected. That's type 2 error. And that occurs when x bar is greater than or equal to c. So here's a picture. It's another bell curve, but notice now the mean is at 140 instead of 150. So C is labeled the same in both pictures, but the center of the bell curve is different under the null hypothesis than it is under this particular true population mean of 140. We do a similar calculation though. We know that the area to the right of C has to be 0.10, so we do 1 minus the normal CDF for the z value of C. And then we solve it for phi, take an inverse normal CDF to get 1.28, and then solve that for C finally to get C equals 140 plus 32 over the square root of n. We now have two equations with C and n, so we can solve those simultaneously. And for example, we could just equate them. And if we do that, we get that n is 53.5 and c is 144.4. Of course, when we're choosing sample size, we always want to round up, even if we're close to the next lowest integer. The reason is that when you increase sample size, you reduce the probabilities of those errors. And if you were ever to round your sample size down, you'd potentially be increasing those chances of errors, and so that you could violate those thresholds that we set for alpha and beta. Overall, we conclude that a sample size of 54 will ensure that the probability of a false positive is less than alpha equals 0.05, and that the probability of a false negative when mu equals 140 is less than beta equals 0.10.